All right, think about this for a second. The very same science that's letting you focus on the words right in front of you is also what makes a star twinkle millions of miles away. It sounds kind of crazy, right? But today, we're going to connect the dots. From the tiny, powerful lens in your own eye, all the way up to the giant lens of our planet's atmosphere.
Yeah, I mean, how are those two things even related? Your eye and a star? It might sound like poetry, but the answer is pure physics. The exact same principles are at play, creating the world you see up close and the grand illusions you see in the night sky. So let's dive in and find out how.
So, first things first, let's talk about that amazing piece of engineering you have right in your head, the human eye. We totally take it for granted, but it has this incredible, almost magical ability. It's like a built-in superpower you use every single second. And the name of this superpower? It's called the power of accommodation. See, the lens in your eye isn't static. It's constantly and automatically changing shape to adjust its focal length. It flexes to look at your phone, then it relaxes to look out the window, all in a fraction of a second, just to give you a perfectly sharp picture of the world.
But, like any superpower, it's not infinite. There are real physical boundaries to what even a perfectly healthy eye can do.
That first limit is something called the near point, and you can actually find yours right now. Just take your finger and bring it closer and closer to your eye. You see that spot where it suddenly gets blurry and you feel a little strain? Bam! That's your near point. It's the absolute closest your eye can comfortably focus. For most of us, that point is about 25 centimeters, or around 10 inches away. And this isn't some random number, it's pretty much the industry standard for a comfortable reading distance. Try to get any closer and the tiny muscles in your eye just can't contract enough to bend the lens into focus. They've hit their limit.
Okay, so if the near point is just 25 centimeters away, what about the far point? How far can we see? Well, for a normal, healthy eye, the far point is infinity. That's right. Your eye is literally designed to effortlessly focus on things that are light years away. Your personal field of vision stretches from the length of a ruler all the way to the most distant stars in the universe. Pretty amazing.
But what happens when this incredible focusing system isn't quite working perfectly? Well, that's where you get into refractive defects, really common conditions that I'm sure you've heard of. So, the two big ones are myopia and hypermetropia. You probably know them as nearsightedness and farsightedness. With myopia, you can see things up close just fine, but distant stuff gets blurry. That's because the eye is focusing light in front of the retina. With hypermetropia, it's the exact opposite. You can see distant things clearly, but nearby objects are blurry because the light focuses behind the retina. It's all about where that point of light lands.
And then there's a third one called presbyopia, which a lot of people start to notice as they get older. Remember that power of accommodation? The lens's ability to flex and change shape? Well, as we age, that lens gets a little less flexible. So this isn't about the shape of your eyeball. It's all about the lens itself starting to lose its focusing superpower.
Okay, so we've got how the tiny lens in our eye bends light. But now let's scale this idea way, way up. What happens if the lens isn't a tiny piece of tissue inside your eye, but the entire blanket of air that surrounds our planet? This is where things get really cool. Earth's atmosphere basically acts like a giant, imperfect, and constantly moving lens. And because of that, it creates some truly spectacular illusions for us down here on the ground. The scientific principle here is called atmospheric refraction. When light from space hits our atmosphere, it has to travel through all these different layers of air. Some are warmer, some are colder, some are denser. Every time the light passes from one layer to another, it bends just a little bit. So its path is constantly changing before it even gets to your eye. And what's the most famous, most beautiful effect of this atmospheric refraction? You guessed it, the twinkling of stars. It was never the star that was flickering, it's an illusion created right here in our own backyard, atmospherically speaking. Think about it. Light from a star travels in a perfectly straight line for millions of years through the vacuum of space. But the second it hits our atmosphere, that straight path gets bent. So from where we're standing, the star actually looks like it's in a slightly different position than it really is.
The process is actually pretty straightforward. Stars are so incredibly far away that their light reaches us as a single tiny point. As this one little point of light travels through all the turbulence and shifting layers of air, its path gets bent randomly and super fast, and our brain just interprets this chaotic, flickering light as a twinkle.
And hey, this is also the reason why planets don't seem to twinkle. You ever notice that? It's because they're so much closer to us. They aren't just single points of light, they look like tiny little disks. So you can think of their light as a whole bundle of rays. And while each individual ray gets bounced around a bit, the overall effect gets averaged out, giving us a nice, steady glow.
But the twinkling of stars isn't the only trick our atmosphere plays on us. It also affects the biggest, most important object in our sky, the sun. And believe it or not, it actually changes the length of our day. Our atmosphere literally bends sunlight around the curve of the Earth. It's wild. This creates this amazing illusion, where at sunrise, we see the sun's light coming over the horizon before the sun itself has actually physically risen. And the same exact thing happens at sunset. We see a kind of ghost of the sun for a few moments after it's already dipped below the horizon.
So how much of a difference are we talking about? Get this, it's about 2 minutes. You see the sunrise 2 full minutes early, and you see the sun set 2 full minutes late. When you add it up, atmospheric refraction is giving us about 4 extra minutes of daylight every single day. It's a daily illusion you can literally set your clock to. So there you have it. From the power of accommodation happening inside your own eye to the atmospheric refraction of starlight, it's all the same basic principle: right bending when it passes through a lens. One lens is biological and tiny, the other is planetary and absolutely massive. But the science connecting you to the rest of the cosmos, it's exactly the same.
It really makes you think, doesn't it? Our entire perception of the universe is being filtered and changed by the very air we breathe. If it can create ghost suns and make stars twinkle, you have to wonder, what other incredible cosmic illusions are out there, hiding in plain sight?